The following content is supported by victoris.org.
Now for the next question, we're given the experiment that measures the gravitational constant g. Personally, I find this quite amusing that we can actually determine the gravitational force with the apparatus and the length scale that we work with. And Henry Cavendish actually got it to quite a close value to the actual amount that we measure today. So the whole idea is that torsion wire and two masses in this way, we can actually use gravitational force to attract one of the masses, and when it rotates, we can actually measure the angle at which it rotates by, hence obtaining the gravitational constant. So the first part of the question asks us to find the torsion coefficient in terms of the period of oscillation. Now this isn't too hard to do because these masses are basically point masses and the axis of rotation is just the center axis. Since we know the length of the rod is L, the distance from the point mass to the center axis is just L over 2. Summing them up would just give us ml squared over 2. Now when the thing rotates, there will be torsion applied on the wire. Think of it as a twisting force on the wire. This torsion will restore the masses back to its original configuration where it's in equilibrium, and the restoring force is kappa theta given in the question over here. And on the other side, the torque is also equals to I alpha. Rearranging this equation gives us this, which we see as the form of SHM. Substituting the value of I we had inside into this equation will give us the following expression. Simplifying it down will give us this. It is important that we remember the form of SHM, which is always the second derivative of a quantity is minus omega squared of that quantity. Now in part 2, we are putting a massive object near our small masses, and the gravitational attraction would cause the small mass to move towards the large object, hence resulting in an angular displacement θ1. Now the first part of the question is just a giveaway. They are telling us that the separation between the large sphere and the small sphere, the air gap in between them is 1 millimeter, and they're giving us the diameter of both the big mass and the small mass. Then they want us to find the center to center separation, which is just taking the two radius plus the air gap. Ideally, you should try to get these marks in the exam because they are giveaways. Now in part 2, we are told that the rotation is too small to be measured using a protractor, so instead they sought to find the displacement of the small mass, and by using information of the length of the small mass to the center, you can calculate the angular displacement. θ1 is just given by the displacement divided by the distance, which by substituting in the values gives you the following expression. We are also asked to estimate the uncertainty. So because this is a division, the percentage uncertainty adds up. So we need to find the percentage uncertainty for both quantities, and substituting in the values given in the question, we obtain the following expression. Now the next part is where the fun begins, where we can start to calculate the gravitational constant g from the above information we have derived. So the main step is to note that in this case, when the object is in equilibrium with the big mass beside it, the gravitational force provides the torque about the center axis, which is what causes the whole system to be the torsion, and the torsion force in the wire is trying to restore it back to its original equilibrium. Now because in the previous part we have derived torsion in terms of the period t of oscillation, this gives us a way to determine the torsion and hence determine the force of gravity. The steps are as follows. The gravitational force provides a torque of this amount, and the torsion provides a torque in the opposite direction. Equating the two gives us this, and rearranging it gives us this. We have now expressed the gravitational constant g in terms of the period, and the period is something we can accurately measure over many oscillations. Now in part B, we are given a slightly different scenario. Instead of measuring the displacement of the small mass, we now want to read the angular position of the setup by using a laser and a mirror. This is more accurate. We can put a measuring apparatus over here on the screen and measure it on the screen directly instead. Now something to note is that when there's angular displacement of θ over here, the laser reflected will have moved angle of 2 θ. To convince you of that fact, just imagine that you have the mirror over here and the laser beam shining perpendicular to it. The laser beam returns at an angle of 0 degrees, and that is expected. Now what happens if I rotated the mirror 45 degrees? The incoming beam, like this, will be reflected at an angle of 90 degrees. And if that's not enough, you can see that if the mirror was rotated at the angle of 90 degrees, the incoming beam basically glances the mirror and shoots off at 180 degrees. I hope that these examples are enough to convince you that the angle of the laser beam deflection is twice the angle of the rotation of the mirror. Without this expression, everything we calculate will be off by a factor of 2, and the final answer would be off as well. So with that out of the way, you need to find the rotation θ2 of the small masses in terms of how much the laser beam has deflected on the screen. The mirror is 12 meters away from the screen. That gives us this length. and we know that the deflection of the laser beam on the screen is 15.6 cm. That gives us this length. This lets us find the angle of deflection of the laser beam itself, and we take that divide by 2, that will give us the angle of deflection of the masses. Putting it in terms of equations, we get the following expression and value for theta 2. Now the professor proceeds with the experiments. He removes the giant masses and start measuring the period of oscillation. Now looking at the expression we have for G in terms of the period of oscillation, with the answers over here that we want to obtain. So R squared, M are all values that we have given in the question. Theta 1 is the value we obtained from the laser experiment, and T is the period that is given in the question. So it just amounts to substituting all those values in correctly, and that gives us the following value for G. Do note there's something important to note over here, which is that the time measured in the question of 10 minutes and 22 seconds is actually 3/4 of the period, because the time measured in the question was going from maximum deflection through the equilibrium to opposite maximum deflection and back to the equilibrium position again. If we were to put the 3 parts over here, where these are the maximum deflection points and this is the equilibrium position, then what that means is that the professor starts recording time over here, and it goes here, and it goes here, and it goes back over here, and he stops the timer at the equilibrium position. If we plot the graph of position out, we'll see that it has only completed up to this point, which is 3/4 of the entire period T. Hence, it's important to divide by 3/4 to obtain the actual period for the oscillation. The good thing about this question is that if you obtain a funny value for G, then it tells you that your calculations are slightly off and you can go back and see where you went wrong. Now the professor leaves the laser on and lets it continue oscillating, and we see that the next time the beam passes through the equilibrium position is this. Now given this value, how are we supposed to know how many times the system has oscillated? The answer is that we don't. We let the unknown value be n. That gives us the following expression for the period. Now because we don't know the exact value of n, what we can do is we can take the original value of t that we calculated in the previous question, which is 829.33 seconds, and then we take the quantity on the right hand side over here divided by t, and we see that most appropriate value for n is when n is 60. If n was chosen to be any other value, then the t that we obtain will be further off from the t we obtained in the previous step. Because the period of oscillation must be the same in both scenarios, we can infer that the t obtained in part 3 is the more accurate period than the period obtained in part 2. Hence, part 3 gives us a refinement of the period from part 2 by letting the system oscillate many more times and taking the average. This gives us the following expression for t, and we can see that the value of t over here is not too far off from that obtained in part 2. Now the professor uses the new value of G calculated from part 3 and finds that it is slightly lower than the accepted value of the real G that we know of today. Reason for this is that because the experiment was conducted in the air resistance will actually damp the oscillation, causing T to increase. And we know that when T increases, when we look at the expression over here, when T increases, G would decrease. That's why he obtained a lower value of G. That concludes question 5, and let's move on to question 6.